In this video, we're going to look at integration by inspection. This is looking at doing integrals that aren't completely standard integrals, but are integrals of expressions that we will arrive at if we differentiate something using the chain rule. So really, we're trying to reverse the chain rule in cases where we hope we can spot what we might have differentiated together. In order to do that, we're going to have some chain rule results ready to notice and ready to start from. The first one of those that we're going to look at is if we have any function which is of the form stuff to the power of n. So by stuff, that could be x squared plus 1, it could be 3x plus 5, it could be anything there, a polynomial or something more complicated, even like sine 2x. So if we've got something like that, when you differentiate using the chain rule, so this is going to be just a specific case of the general chain rule, you'll always end up with your stuff differentiated multiplied by your n multiplied by your stuff to the n minus 1. That's what we're looking for. So if we get something of roughly that form that we want to integrate, we know what we're expecting to end up with. Okay, let's look at this in a couple of situations then. So the first example I'm going to look at here is what to do if we're asked to integrate 2 brackets 5x plus 7 to the 4. Now, if we're ending up with 5x plus 7 to the 4, well, what power of 5x plus 7 might we have started off with that would give us this? Well, if we've ended up with a power of 4 after we've differentiated, and remember, integration is just reversing differentiation, we'd have to start with something to the power of 5. There's going to be other bits here, but always going to structure these questions in a guess and check style. We're going to try something that we're expecting to give us something close, and then we can adapt it as we need to. So the guess I'm going to suggest we make here is let's think about if we had 5x plus 7 to the 5, because when we differentiate that, we at the very least know that we're expecting to get something to the 4, which is what we want. We're going to get to other things as well, but we'll worry about that and deal with that as we need to. So our check is we're going to try and differentiate this, see what we get, and make any changes as necessary. So when we differentiate this, well, we're going to get stuff differentiated. Well, 5x plus 7 differentiated is just 5. Multiplied by your n, which again is just 5 in this case, multiplied by your stuff to the n minus 1. So here is going to be 5x plus 7 to the 4. And, well, this is just the same as 25 5x plus 7 to the 4. No, sorry, I missed a bracket there. So let's look at what we were hoping for. We've got a 5x plus 7 to the 4 we were hoping for, but we've ended up with a 25 we were hoping just to have 2. Well, how does that suggest we could change our guess? What we can do, and there's a fairly simple solution here, if we want 2 and we've got 25, we know we want to multiply what we end up with by 2 over 25. So we can just say, well, let's do that to our guess. Let's multiply our guess by 2 over 25. And this tells us that our actual answer here is just going to be 2 25ths of 5x plus 7 to the 5. And then we shouldn't forget our plus c because we don't have any limits. We've got our constant of integration there. So we start by making a guess of the bit we're expecting to appear without worrying about the extra bits, the 5x plus 7 to the 5. Do our check and then make any corrections. We can only make a correction if we're multiplying by a constant. If you find you're having to multiply by x or something like that, then that would change the differentiation a lot because you'd then need the product rule to differentiate your guess. So we can only make our change if we're multiplying by constants, but if we're doing that, then it's nice and easy to do so. Okay, let's look at another example, getting of the same vein, but getting a little bit harder now. So what about if instead we're asked to integrate 3x brackets x squared plus 4 to the power of 9? In this case, we might be tempted to think, well, hang on, we're in trouble, there's an x on the outside here. The reason we're going to be okay in this situation is because if we look at our stuff, we've got a stuff to the 9 here at the moment. Well, when we differentiate that x squared plus 4, we're going to get some multiple of x, which is what we've got on the outside. We don't have the right multiple of x on the outside. But again, let's not worry about that yet. Let's make our guess scene roughly what we're expecting, and then we'll make any changes as we need to. So what guess should we make here? Well, for our guess, let's say we want to end up with x squared plus 4 to the 9. Let's start with x squared plus 4 to the power of 10 and adapt from there. So if we do our check here using the chain rule, sorry, I can't spell. So if we do our check, then we're going to get our stuff differentiated, which is 2x, because x squared plus 4 differentiated is 2x, multiplied by Rn, which is 10, multiplied by our stuff, which was x squared plus 4, to the power of 9. Now, let's simplify that. Let's get it all together. So there's 20x brackets x squared plus 4 to the 9. And now let's compare with what we wanted. Again, we've got this x squared plus 4 to the 9. Perfect. We're really happy with that bit. And we've got our x. We're happy with that bit. But we've got this 20 and we wanted this 3. So we do need to make a correction. Well, what correction can we make here? If we've got 20 and we just want 3 lots of them, we want to multiply this by 3/20. So that's exactly what we'd want to do to our original guess. And our answer is just going to be 3/20 of x squared plus 4 to the 10. And again, let's make sure we remember to put plus c in there and get our constant of integration. So making a guess, and we were happy to have the x on the outside this time. This question, we wouldn't have had a really nice quick way of doing if we hadn't had that x on the outside, because we'd have had to divide our guess by an x. But because it was there, it all worked out and we just needed to change that constant. All right, so that's if we integrate in something that's roughly of the form stuff dash times stuff to the n minus 1. What other situations might we look at? Well, the other cases that we might need to be aware of are sine and cos. So the next situations I want to consider here is we want to be aware what happens if we differentiate sine of stuff. Well, if we differentiate sine of stuff, our chain rule tells us that we get stuff differentiated times cos of stuff. And if we want to differentiate y equals cos of stuff, then we get negative stuff differentiated times sine of stuff. So if ever we find ourselves dealing with something that looks like stuff differentiated times cos of stuff or stuff differentiated times sine of stuff, we can deal with the negative as we need to. Then we can hopefully use the same guess and check idea. So let's have a look at an integral where that's going to come into play here then. So as an example here, let's think what happens if we want to integrate x times cos of x squared dx. In this situation, so we've got cos of x squared in there. So our stuff in this case would be an x squared. And stuff differentiated would be 2x, which is pretty similar to what we've got on the outside. Okay, we don't have a 2, but constants we can deal with. So if we want to end up with a cos of x squared, we're going to need to start with the sine of x squared to have a chance of ending up with that. So let's make our guess here to be sine of x squared, and let's think about what happens when we differentiate this. So if we do our check here, well, what are we going to get? We're going to get stuff differentiated, which is 2x, times cos of x squared, which is really pretty close to what we want. We've got a cos of x squared, perfect. We've got the x perfect. We've got this 2, which we don't want there. So we just wanted one lot of cos of x squared. So ideally, we want to multiply our check by half. So if we multiply our guess by half, again, we're okay because it's only a constant we're multiplying by. That tells us our answer is a half sine of x squared. And then again, plus c for our constant of integration. What other situations might we have? There's 2 more situations I'm going to try and get through in the next 5 minutes for you. So What if we have y equals e to the stuff? What's our rule for differentiating that? Well, if we do the chain rule on this, we end up with dy by dx is stuff differentiated times e to the stuff. So let's try tackling this one then. So if we want to integrate, I'm going to go for something relatively simple in this one as an intro. But this is going to be another example. 2 times e to the 5x plus 1 dx. If we want to end up with an e to the 5x plus 1, we're going to have to start with an e to the 5x plus 1. It'll give us other stuff as well, but let's worry about that once we've made our guess. So we're going to make our guess of e to the 5x plus 1 and see what happens when we differentiate this. So when we try differentiating this, let's do a check. Our stuff is 5x plus 1. So when we differentiate 5x plus 1 differentiated, it's just 5, and we'll get 5 e to the 5x plus 1. Now, again, we've got this e to the 5x plus 1, which we wanted, but we've got this 5. We didn't want this 5. We wanted the 2. So what do we need to do? We need to multiply by 2/5. Again, that's fine because we're just multiplying by a constant. So our answer is going to be 2/5 e to the 5x plus 1. And as always, we need to remember that plus c in there. Final situation I want to look at, which is probably the hardest to spot, which we haven't looked at so far, is what happens when we've got natural logs. They're the most unusual of the lot. They can be a bit hidden in here and you need to watch out for them. So if we have something of the form ln of stuff, so again, something like ln of x squared plus 1 or ln of 3x cubed minus 2x squared, could be as complicated as you like there. dy by dx is going to be stuff differentiated over stuff. So if you're asked to integrate a fraction and the numerator looks roughly like your denominator squared, this is what you're going to want to try. So let's have a look at a situation like this. So if we want to integrate 3x over x squared plus 1, we've got reason to be encouraged here because our numerator is almost our denominator differentiated. Not exactly, but it's pretty close. So let's try guessing. Our stuff on the denominator is x squared plus 1. So let's try guessing here ln of x squared plus 1. So if we make that our guess here, I would say, if depending on how much work you've done with natural logs, you might want to put a modular sign around the x squared plus 1. I'm not going to worry about it in this video, but if you're thinking I should have a modulus around that x squared plus 1, you're right. In an exam, in an A-level exam, you are going to want to do that, but I'm not going to worry about that just now. So when we try differentiating that, we're going to get stuff differentiated, which is 2x over stuff, which is x squared plus 1. And now let's compare with what we've got. Our denominator is perfect. We've got x squared plus 1 there. Our numerator, we've got 2x. We want 3x. So what can we do? Well, we want that denominator to be 3 over 2 times bigger. So we want to multiply our check by 3 over 2, which means we want to multiply our guess by 3 over 2. And our answer is going to be 3 over 2 ln. And at this point, I'm going to put the moduluses in, but if you don't know why, don't worry about that for now. You will get up to that, and then we've got our plus c there. So a whole bunch of situations to look out for, various situations to watch out for, but overall, if you're looking for something, if you got to something to the power of n minus 1, and the thing outside is some multiple of the stuff inside differentiated, make it increase the power and make that your guess. If you've got a sine and a cos involved, there's only one natural guess, but again, it's only going to work if the thing outside is a multiple of the thing inside differentiated. E to the stuff's probably the easiest thing to recognize and you just keep it as e to the stuff and differentiate. The ln ones are probably the hardest to recognize because you get given a fraction, it's not natural to think about your natural logs there. But if your numerator is very similar to your denominator differentiated, give or take a multiple, make that your guess and go from there. Thank you very much.